All right, hello and welcome to Gears of Resistance, episode number 2. Last week we discussed things about the difference between a microcontroller, single board computer, um, basically the difference between an Arduino and a Raspberry Pi, and we also talked about field programmable gate arrays, FPGAs, which are just starting to get into the maker market. Um, with things like the Papilio, and there's another one I can't remember the name of it on the top of my head, but I think it's in the show notes from last week. So basically, there's different types of boards. Each have their pros and cons depending on the application. And I encourage you to look at last week's episode if you've got questions. So with that, this week we're going to kind of take a step back and we're going to talk about some really fundamentals. We're going to talk about voltage, current, resistance, power. What is it? And we're not trying to do it from like you're trying to get an electrical engineering major. We're going to talk it just about enough so that as someone who's getting into electronics, you'll know just enough of what to look for on data sheets and what kind of questions to ask before you start hooking components up and frying one. So with that, I'm going to turn it over here to my, let's see here, if I can switch over to my other camera here. Boom, 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 bear with me. Okay. All right, make sure I know how far up I can. Oh, there it goes. So I'll make a little note for myself here. Don't go any higher than that. And then let me turn this off too here. I'm going to turn off the lower third. Okay. And then hopefully it will. There we go. So let's start with, oh man, this camera just wants to keep going out of focus and in focus. So let's start with voltage. Obviously, it's measured in units of volts. And sometimes we abbreviate that usually as V. So what is voltage? Voltage is a potential difference. So you have to measure voltage from 2 points. It's not like current where you can kind of measure at a single point. What it is basically think of your battery. At one end, you have potential. Say in the case of a AA, AAA battery, it's 1.5 volts at the one end and 0 volts at the other. It's the ability to do work. So without voltage, without a potential difference of electrical charge, you can't push current to flow. The way to think about it, and this is the way I was taught. Now, this is the famous water analogy. Now, I'll get a lot of hate mail because, yes, water is not an exact, the analogy, it doesn't hold perfectly. But if you think of a big barrel, and if it's filled up with water, the more water in that barrel is equivalent to more pressure at the bottom. If I had a little valve out here. So this is the same thing if I made this into a battery. So we'll put the little terminal up here. Different batteries, different sources of energy, different energy sources have different voltages. So the way to think of it is kind of think of it as that level in the barrel of water. More water, more pressure at the bottom. So that's, again, it's not a perfect analogy, but to get your head, when you're just starting out to get your head, think of the voltage as equivalent to a barrel of water. And the more water I put in it, I have more pressure at the bottom. That means I can push more current through. So basically, and again, the pressures I have to measure, it's always in relationship to 2 points. So there's the top of the water head and then at the bottom. So same thing with the battery or a circuit. So the symbol, and I apologize if you're listening to this, that's a multi-cell battery. That'd be like a 2-cell battery, 2 AA's in series. So a battery is just this, though. a single battery. Sometimes they put the little plus sign to indicate which end is positive, which end is negative. Okay, I want to save a little bit for when I get into current, because there's how current flows. There's some differences in terminology, but just so for now, do you know what a symbol for a battery is? If you see, again, a multi-cell battery, it just means it's multiple batteries in series. These produce what's called direct current. Battery produces direct current, means current flows out one terminal and into the other, and it does not go in reverse. It's always one direction. It'll be compared to alternating current. And we'll talk a little bit about AC today, but not too much. We're going to stick with DC for right now, because when you're just starting off, there's probably very little AC work that you'll do. Trying to think if there's anything about the voltage else we want to talk about. The symbols, it's measured in volts. Batteries tend to produce them, tends to produce DC. There's other sources of DC that we can talk about a little bit later. But for right now, what most people are going to use is a battery. Now, your microcontroller board will probably have a +5 volt, or sometimes it's listed as VCC ports. It's taking the AC that comes out of your wall and stepping it through some electronics to produce the DC, but we're not going to talk about those today. Today we're just going to focus on the basics. So let's move out of voltage and let's move into current. And again, we're going to focus on direct current today. So let me go get my other marker back here. Where did it go? I lost my red marker. All right, we'll just go stick with the blue then. So let's next talk about current. So current is measured. Oops, let me bring that back here. Apologize. It is measured in actual amperes, though it's often shortened to just amps. And even with that, when the kind of currents we're talking about, usually we're talking in the milliamps, which still under the right conditions is enough to stop your heart from beating. So, always, no matter what you're doing, even if you're not doing considered high voltage work, always be careful. And we'll talk about safety as we move along. That's usually also abbreviated MA. So when you look on your spec sheet and you look for current, you'll usually see it rated in either milliamps. There's also microamps. And today, really, for things that really sip energy, there's even nanoamps. So those are what you'll see. So either amps, milliamps, microamps, nanoamps. Usually you're going to see milliamps in our world. So what is current? Current is the flow of electrons through a wire. So again, like we talked about voltage, you need a source of voltage, you need a potential difference. And then if you close that loop, if you connect basically the positive terminal to the negative with a wire, you will get, and this is where we talked about earlier, there's some different nomenclatures, little electrons race around. Now, here's where it gets interesting. We have this to thank to, at least the way I understand it is, we have to thank Benjamin Franklin for this. So we always thought that in the universe, in the world, everything goes from from something of higher potential to lower potential. Pressures, temperatures, things tend to even out by flowing from high to low. So we thought that same thing would be hold true for electricity, that there would be a positive terminal, there would be a negative terminal, and current would want to flow from the positive to the negative. Reality, if you take a, say you take a, and we know that, let's start, we know that these are electrons, right? So electrons are negatively charged. And I do apologize because you probably can't see this. Let me redraw this up here. So like I was saying, we have battery connected with the wire. You get electrons to flow. Now the question is, which way are they flowing? Like I said, typically you'll see a battery marked with a positive terminal. You can then assume that the other terminal is negative. And based on what Franklin proposed, we would assume that the electrons would flow out of the positive terminal of the battery into the negative. And in fact, this is what we call conventional, I can't spell IONAL, conventional current flow. But here's the reality, and this is where I was going with my magnets. Say you take a magnet. We all know they are north and south poles. And if I put another north to south, like this, now I have a south and a north facing each other, they're going to want to come together. They're going to want to attract. I want you, you want me, we come together. Now, likewise, if I were to put two south or two north facing poles together, what happens? There's a repulsion. They don't like each other. They want to go their own separate ways. So if by thinking that through, electrons are negatively charged, if it holds true that likes repel and opposites attract, then that means the electrons are getting sucked into the negative. So the negatively charged particle is being attracted to the, oh no, that can't happen. So so if you were to actually get down at the microscopic level and you could actually see electrons racing around the circuit, you would actually what's called electron current flow. Now, so in other words, in reality, in the physics of how it really works is the electrons are stored down here in the negative terminal. When there's a circuit completed, they're repulsed from the negative and they race around and they get attracted up to the positive. The cool thing is the math works out regardless, so long as you're consistent. So what you're going to see a lot of times is the conventional current flow. You're going to see people draw it out to there's the battery, and then I'll introduce the new symbol, the resistor. And they're going to say that the current flows this way. And that's cool. It works. The math works. You just have to realize that if you have multiple circuits, that you treat each one the same, that you don't sometimes do conventional current flow, and other circuits you do electronic current flow. So as long as you stay consistent, you're fine. From a safety perspective, it is the current that is dangerous. Current is what killed. There's an old saying that was taught to me, was that volts jolt, mils kill, milliamps. So the other thing, we're going to kind of bring this together now. So when you're doing electronics, before we get to the resistor, your parts are going to be spec'd in, a voltage, sometimes Vmax. And there's going to be, and then a max current, a forward current. The thing to remember is, so let's say we have a device A. It's got a little output here. And we want to play with device B as an input. You have to make sure that the voltages, the output voltage, and the input voltage are the same. So if device B says I take 3 volts, but device A says I output 5 volts, you have a problem, or vice versa. The voltage between devices has to match. Not so with current. So let's assume now both devices are 5 volts. So we can go ahead and connect a wire. Boom, we're fine. Now, the other part, assuming that is, let's say this guy says, I need, based on my circuitry, this is a black box, I will draw 100 milliamps. So long as device A can source 100 milliamps, you're cool. If it can source more than that, if it can source 500 milliamps, that's fine. In fact, now what you could do is actually have 5 device Bs all connected for the same device, because each one would consume ... here. I did it again. So let me redraw this up here again. So if device A, my output device, does 5 volts output, and it can source 500 milliamps, then I can have 5 device Bs assuming each one requires, again, 5 volts at 100 milliamps. So I could divide out into each one, because each one would draw its 100 milliamps. We're all working at 5 volts. The electronics inside will suck down the current it needs. So, long story short, always make sure that the voltages between 2 devices matches, or you need to do some sort of circuit in between to translate between the 2 voltages. And there's actually chips that do that. So like Arduino is 5 volts, Raspberry Pi is 3 volts. So things that were built for Arduino won't directly work with a Raspberry Pi without some conversion. So the easy, quick, dirty way to do that is to say we have an Arduino sensor that it puts out 5 volts. You want to connect that to your Raspberry Pi or some other 3 volt tolerant. If I go directly into it, at best case, I fry that particular GPIO pin. Worst case, I fry the whole board. Now, the nice way to do it, the best way to do it, is to get a little level converter chip. And depending on, again, which voltages you're, they're also called level shifters also. So depending on what voltages you're going to and from, and sometimes you have to also be careful because sometimes they're unidirectional, they only go one way, and other times they are bidirectional. And I would encourage, just to be safe, always pick up bidirectional ones that can translate both ways. So what you do is you would tie ground into both the voltage or the data line, and now the 5 volts here gets translated to the 3 volts. I guess it would be the other way around. But the point is, it shifts between the two. Let's assume, let's say you're quick and dirty, you need something real fast, and you're only concerned about going in one direction. What you could do is, let me make some room here, do a voltage divider circuit. But to do that, we need to get into resistance. So voltage, current, voltages have to match. Current, you have to make sure that the device that you're going to be drawing current from can safely source the amount, and preferably more than, because your circuit will only suck in the current it needs. Now let's talk about resistance, because we can't talk about the circuit before we do. So I drew back here in the earlier one. Oh man, I really hate how this thing keeps going in and out of focus. Let me see if I can get this to work. There we go. So again, the battery, which will be rated with a voltage, say 5 volts. The other, I guess I should really back up. It will also be rated in a what's called milliamp hours, or HR sometimes, which is basically how much energy it has stored. So in other words, let's say this battery has 1,000, was rated at 1,000 milliamp hours. Well, if you do the math, 1,000 milliamps is 1 amp times the hour. So in other words, if whatever load I have out here drew 1 amp, this battery would be able to keep this load powered for 1 hour. That's, not probably realistic, but because drawing an amp is a heck of a lot of current, especially in the world of microcontrollers and other small electronics. But anyway, so this load is modeled as a resistor. So let's talk about that now. So resistance. Resistance is simply the property of a material or a device to resist the flow of current. So remember, if I made my battery here and I just connected to the wires, I'd get a short circuit. And eventually I'd probably, if it was a real thin wire, it would probably break apart, if not catch on fire. So same thing though with, not just short circuiting is an extreme example, but you always have to limit device of the current draw to any component. Every component has a current rating, as well as a voltage rating. So let's assume that we have like some lamp out here that we want to power. And that's a little symbol for the lamp. And if I put the 5 volts directly across that lamp, chances are it would burn really bright, and then poof, the little filament would get too hot and crap out. So this is more, in electronics, we'll probably replace this with an LED. But for right now, to make it simple, without talking diodes, we're going to just use a little lamp. So I need to put some amount of resistance in series. Now, real quick, let me also say, I believe that though this symbol is the one I've always seen and used, and I think it's called, I want to say it's the American symbol, but just so you know, there's another symbol for a resistor, and that's simply a little rectangle, and I think that's maybe the SI unit or the something equivalent symbol, the international symbol. So just be aware that resistors come in two symbols. I'm going to use the little squiggly, since to me that is just always what I've seen and used, and so I'm going to stick with it. So a resistor introduces resistance. Now the reality is every component, and we're going to talk about some of them, capacitors, inductors, even the wire has some level of resistance. It may be very small, but almost everything has some level of resistance where it wants to resist electrons from flowing. Resistors are specifically built. Now, we're not going to talk, there's tons of types of resistors, different ways they're manufactured. But what we're going to focus on is simply little, maybe carbon or little wire wound stuff that you would kind of get at Radio Shack when you go pull out the resistor bin. So resistors are measured in ohms. OHM. They also, the symbol a lot of times will be the, I believe it's the Greek symbol for omega. Someone will correct me if I'm wrong. Let me think what else. A lot of times you'll see them rated as kilo ohms with a little K in the front, or with a big M for mega ohms. Mostly in electronics, small signal, it's going to be ohms, like 200 ohms, 220 ohms, or 10 kilo ohms. The other thing they import is like that. It actually took me a while after I was well into my undergrad to realize that, you know, when you sit here and you do all the math and you figure out you need a 327.86 ohm resistor, and you go, you know, if you're an engineering student or a new freshman in engineering, you ask your technician for that size resistor, they're going to laugh at you. Reality is resistors are only manufactured in very discrete quantities. So 220, 10 kilo ohm, 5 kilo ohm. If you have an application that requires a very precise resistor, you'll have to add resistors together in different combinations. Usually it suffices to say that, say you calculate that you need 213 ohms, then you go grab a 220 ohm resistor, you'll be fine. That's where, you know, electronics is more art than science. So that's why you prototype stuff. But anyway, so I guess at this point, to really be able to solve this question of, you know, okay, I need a resistor, but what size resistor? We need to, and we've discussed ohms, we need to introduce what's called Ohm's law. So basically there is a relationship between voltage, current, and resistance. And that is voltage equals IR. I is, when you're doing equations, I don't know if I mentioned or not. So while the unit of measure is ampere or milliampere, or milliamps for current, and ohms for resistance, and voltage is volts. When you see the mathematical equations in textbooks or whatever, it's VIR, unit of measure, though V, little m, big A, milliamps, and again the Greek symbol omega for resistance. So what this is telling us is the amount of current times the resistance I'm going through induces a voltage, or I drop a voltage. In this case, so the voltage drop across a resistor is related. The equation is that resistor's value times the current being pushed through it is the voltage drop. Now you can rewrite this in different ways. R therefore also equals, you divide out voltage over the current. So therefore the current is also, again doing the math, V over R. Little thing that I remembered is, imagine the term V is a vulture, I is an Indian, R is a rabbit. Well, if the vulture is up in the claw in the sky, and the Native American is down on the ground, as is our little furry bunny, the rabbit. Now you can see the relationship. The vulture, the voltage, sees the Indian next to the rabbit. So V equals IR. From the point of view of the rabbit, he would look over and he would see the vulture over the Indian. So R, resistance, ohms, is the voltage over the current. And lastly, from the point of view of the Native American or the Indian, it would be the vulture over the rabbit. He would look out, he would see the vulture over the rabbit. Therefore, I, for current, milliamps, amps, equals V over R. Just a little way to remember it. So, going back to our battery and our light bulb dilemma. Again, I would know that I've got a 5-volt source. I would go look at the spec sheet, the data sheet of my component. And let's say that this light bulb has a 4 voltage. Again, I'm using these terms because when you get to LEDs, it'll actually be useful, but to give you the idea. So let's say it has 2 volts, and it has a current, max current through it is, let's see here, let's say it's 10 milliamps. So solve for R, as they would say. So going back to my equation over here, so V equals IR. If I know that 2 volts is going to drop over this light, and my source has 5 volts, that means how much voltage is going to drop over my resistor? Well, if you didn't know, you could just do 5 volts minus the forward voltage. So that would be, you probably see it sometimes written as V battery minus VF, V sub F, over, and again, let me should work this. So I'm looking for R. So I need to rewrite this equation to say not V equals IR, but I'm looking for R. So R equals V over I. 10 milliamps is actually 0.01 amps, because milli is 10 to the negative third. So if I move it back 1, 2, 3 decimal points to the left, that will get me my amperes. And that's the other thing to remember is you have to be always in the base unit or convert to the same unit. So if I put 10 down here, that's 10 milliamps. I would get the wrong answer. So in this case, it comes out to be, so that's, again, let me rewrite that. So 5 volts minus 2 volts is 3 volts. And 3 divided by 0.01, that will come out to about 300 ohms. So again, I would go race to my bin of resistors. I'd look for a 300. I may or may not have it, so I'd have to make do with what I have by going larger. I think like 330. It's 330 standard size. Or what I could do, let's say I had 3 100 ohm resistors. What you could do, and this is again, let me erase this. This is more basic theory, is how resistors add together. So, and let's talk about series and parallel. So I have my battery here. Again, this is really an episode, if you're listening, you probably really need to watch. So if I say I had, again, I only had 3 100 ohm resistors, and I needed to get that, again, there's my little light down here. What I could have done is add 3 100 ohm, there we go, 100 ohm resistors in series. In other words, each of these will experience the same amount of current, and they will each drop, in this case, since all the resistors are the same, they'll drop the same voltage across them. But the equivalent would be no different than if I had just a single 300 ohm resistor. That's series. Now, say you wanted to lower the resistance, or the equivalent resistance. You can also arrange your resistors in what's called a parallel configuration. Now, let's assume, just for the sake of argument, these are all 10 ohm resistors. Now, each one of these, here's the voltage. They're going to see the same voltage on top of each one. Pressing down, again, using that water analogy. And again, because they're just the fact that they're the same resistor value, they'll see the same current. But let's say, for sake of argument, I made this a 100 ohm resistor instead of a 10. So I have 10, 10, and 100. Well, more current would go through these guys because current always takes the path of least resistance. So more current would go through the 10 ohms. A little less current would go through the 100 ohm. But they would all have experienced the same voltage across them. The way you, now you could say, okay, well, what would the equivalent I could replace this with one resistor, these 3, and would that value be? So to solve that, you take the reciprocal of all your, which is basically saying 1 over that resistor value plus 1 over that resistor value of R2. And over here, we'll say that's R3. So plus 1 over 100, we made that 100. Take all that, add it together. Then take the reciprocal of that sum, put it all together. So in this case, it would be basically 0.1 plus 0.1 plus 0.01. And then so that would be the equivalent of about a 4.7, we get 4.8 ohm resistor. Let me just make sure here. Yeah, there we go. So this would give you, you could replace these three resistors with the one. This would be the, again, the parallel equivalent. So now we talked about current, resistors, voltage, the relationship. I will point out well, I guess, yeah. So before they do that, we talked about how to order, how you can do parallel resistors, series resistors. Let's talk a practical application. Again, as I said, we're going to try to do more practical stuff. So back earlier, we had that box A and box B. And we said box A puts out a 5-volt signal for its logic high. And box B only likes 3 volts for its logic high. If it sees 5 volts, it'll fry. So how can we use some resistors? Now that we know that resistors will resist current, and thereby each one drops a little bit of voltage. So how can I use that to my advantage to be able to interface these two devices? There is a nifty, simple little circuit called a voltage divider. I put one resistor this way, another resistor I tie to ground, and then I tie this over here. Now it's a relationship. The voltage is of, well, I guess the relationship, the voltage on the output over here. So if I put 5 volts here, what do I get out over here with my V out over on the side? Well, it's obviously it's related to what values you choose for resistors. And the equation, though, is V out equals V in. So again, the 5 volts will be our V in equals, and let me give these resistor numbers, R1, and this one will be down here is R2. V out equals V in times R2 over R1 plus R2. So if I go ahead and say, let's let R1 be a 5 kilo ohm resistor, and R2, let's let that one be a 10 kilo ohm resistor, what do I get? I get, if I replace the R2, that's 10K. R1 plus R2 is 10K plus 5K, that's 15K. My V in here is the 5 volts. So basically, ten over 15 is obviously, that's, you can rewrite that as 2/3. So 5 volts times 2/3 equals 3.3 volts. And let's make this guy here. Usually it's 3. It is 3.3 volts. I just shorthanded it. So now I have, thanks to my little voltage divider, a quick and dirty way to, and again, it relies on the fact that the signal is only going from A to B. If you need it to do the other way, again, those chips I show you, little level converter chips, level shifters, are another thing for another day, but would do the job for bidirectional communications. So did I see that? So equals 3.3 volts. Okay, so that's a practical application, the voltage divider. So current resistance, voltage, current, resistance, the relationship, practical uses. We now need to talk about power. So power is the rate of energy consumption or production. But for our purposes, usually, we're going to look for basically the power rating of our components. So it is measured in watts, usually abbreviated W, or in our case, again, like there's amps and milliamps. Usually it's milliwatts. So we talked about earlier, you have to get the voltage and the current right. Now, back to our example with the light bulb, where we calculated we needed a 300 ohm resistor. Because we had a 5-volt battery. Oh, that's going to run off, isn't it? All right, let me go back up here. So power. So again, let me draw the little circuit. We thought we knew everything about this circuit, this resistor that we needed. It was 300 ohms. This was a 2-volt light bulb that was going to have a imax current max of, what did we say, 10 milliamps? So man, we thought we knew everything. But apparently there must be something that we're missing, and that's the power rating. So while we knew the resistor value in terms of its resistance, what we also need to know is how much power we expect it to dissipate as heat through this resistor. Because one way of, you have to size it both in terms of the resistance and its power rating, so that you, again, don't get a component that fries when you try to push too much current through it. And that equation is power equals VI. Power equals voltage across the component times the current through it. Now, I'm going to lay a little Easter egg here for a future episode. This is true for DC, direct current. The reality is that the whole equation is actually times the cosine of an angle called phi, which is in alternating current. It's so when in DC, the current and the voltage are in phase. It's possible when you deal with sinusoidal or other waveforms of current and voltage that they actually get out of phase. So your voltage and your current basically aren't peaking at the same time. And that's due to reactances introduced by capacitors and inductors, which, hey, guess what? Segues into where we're going. But for our purposes right now, we're going to assume that, again, we're doing DC. So goodbye, cosine. And we're going to limit with P equals VI. So we knew earlier that this guy is going to drop 3 volts. And we know that we calculated the size to limit the fact that we wanted 10 milliamps through it. So we know it's going to, this guy's dropping 3 volts from here to here. This 3 volts is dropped because the light bulb will drop the other 2 volts. And that's the other, I guess, important thing, is that the sum of your voltages across a closed loop circuit will always add up to 0. So if I have, in other words, if a battery introduces voltage, I go up 5 volts, my resistor drops 3 volts, my light bulb drops the other 2 volts. Therefore, when I come back down, and this is like the ground, I'm at 0 volts again. Conversely, if I had a parallel circuit, kind of like parallel resistors we showed, so I have a current coming out of here. It then branches into these two, and then it comes back together. What this node here, the current that comes into it, so this guy here, has to equal the current going out. So at every node, the current that goes into it, all the different ways that current comes into it, and all the different ways the current leaves, has to equal. It has to be a zero. There is no leftover current that gets stuck in the node. All current comes in, all current goes out. Same thing with the voltage drops around the circuit. All voltage gains must be countered with voltage drops. Anyway, so 3 volts times our 0.01 amps. Again, we're going to stay with our units. We're going to drop 0.03 watts, which if I then do the conversion back, 1, 2, 3 is actually going to be 30 milliwatts. So 10 million. So I need to make sure that the resistor I pick is, oh, let me see if I can get that there. Is that any better? Let me write that over here. So equals 0.03 watts, which is 30 milliwatts. Oops. 30 milliwatts. So when I go to the resistor bin, I have to look for a 300 ohm resistor, but I also have to look for one that dissipates, at least safely dissipates 30 milliwatts. So they'll all dissipate it. It's just whether or not they're intended to be built that way. Reality is, yes. So their resistor values, you'll see there's 8-watt resistors, quarter-watt resistors. So like, you know, 1/8 of a watt is 125 milliwatts. 1/8, yeah, 1/8 of a watt is 125 milliwatts. So I could go out, and that's way, my 30 milliwatts is way under. I could safely, now if I was say I had calculated, I was at I don't know, say 120 milliwatts, and I had a choice between 125 milliwatt and a quarter milliwatt, you know, 250 milliwatts, I'd probably go ahead and be safe and get the larger one. You know, not knowing where my product's going to be used, temperature variations and whatnot, to be safe than sorry. But that's it in a nutshell. That's power. That's watts or milliwatts. You've got to again, when you size components, you've got to make sure that you take into consideration the power, the voltage, and the current. And not just, you know, sometimes you calculate, you want to rush through, you calculate the size of a resistor you need. You just got to take the extra couple seconds and also calculate the power that you're expecting to dissipate. Okay, so that's the easy stuff. That's the fun stuff. There are, let me real quick do some more practical stuff here. So there's the resistor, right? You could have variable resistors, potentiometers. They have a little arrow through them as a symbol. They're usually the little knob looking guys. They have three little pins. And you can either, with your hand or with a little screwdriver, turn them and get a variable resistance. Usually we use ones that go from 0 to 10 kilo ohms. There are, let's see here, the thing that everyone likes to use is little photo resistors. So they kind of look like this. I'll have the little pin here, the long pin at the bottom. They'll have they're cadmium sulfide. It physically looks something like that. Usually I think the symbol is like a little resistor circle around it with a little light, like little arrows indicating light. Same thing. So the more light they're hit with, they reduce their resistance. The darker it is, the more resistive they are. So a lot of times to interface, you'll use resistors in what's called a pull-up or pull-down resistor configuration. So say you have a microcontroller pin over here, and you have your VCC source, and say you have this nifty little cadmium sulfide photoresistor up here. Well, you could just connect it. Let's assume this was a switch instead of instead of that resistor, you have a little switch. Well, the problem is what you've just induced now is called a floating gate. So when this button is not pressed, it's not low, it's not high, it's floating. It's basically, this has become a little antenna now. And so now you've got to actually you got to force this thing to ground when it's not connected. So you put another resistor in, say 10 kilo ohms, maybe even more. Yeah, maybe even 100 kilo ohm resistor, I guess. Because what you want when you do press the button, you want the current to flow back into your micro, not to ground. It's wasteful. But so likewise, let's go back. We'll put our little photoresistor in there. So again, voltage divider. We know this is 5 volts. This is a fixed resistor, so it's the fixed resistor. So it's 100K over some variable plus the 100K. So what happens? So the V in is the 5 volts. So what happens to our V out? Man, I keep doing that. So 5 volts times 100K over V variable plus 100K. So what happens when this resistor gets really, really small? So in other words, when I've bombarded the crap out of it with light, it's 100K basically over 100K. This guy goes to 0. 100K over 100K is 1. 5 times 1 is 5 volts. So basically, when it's really bright in this configuration, I'll see 5 volts in the microcontroller. Likewise, if I make this really dark, this resistance goes to like infinity. So 100K over infinity is practically 0. 5 times 0 is 0. Therefore, I see about 0 volts on the pin when it's really, really dark. Now, if I wanted to do vice versa, swap that around. Let's say I put the fixed resistor up here, 100K. Man, that's sloppy. Put that at 100K right there. Put my variable resistor. We'll just use a variable resistor. So now the equation is, it's not V. What did I do V? I did V last time. Strike that. It was R. R variable over 100K plus R variable. So now what happens? I crank this down so I've got a really huge amount of resistance across this. Let's say this thing's capable of doing mega ohms worth of resistance. So huge resistance over a huge resistance plus a little bit is, this kind of just doesn't matter anymore. So it's basically big over big. Is 1 5 times 5 times 1 is 5. So basically, when this resistance gets really high in this configuration, I'll see a 1. And if I crank it down and go to the other way, if it's really, really low resistance, well, 0 over 100 is 0. 5 times 0 is 0. So in this case, when I've got really low when I have a really low resistance, I'll see 0 volts. So depending on what you're building and how you want logic highs to be and logic lows, you can swap your variable resistor with the fixed resistor and whatnot. Another thing also sometimes to consider is if you do have a variable resistor, sometimes you may want to add just a real small value for a fixed resistor, say 100 ohms, just to give give it a little bit of protection and a little bit of signal, even when this guy gets cranked one way or the other. Let me see. I'm trying to see where I'm doing one time. I think I was going to do resistors and inductors today, or inductors and capacitors. I think I'm going to save that for next time. Because I think we are probably way past most people's tolerance for listening to me jibber jabber. Let me crank this back over to here. All right, let me save that. Boom. Switch over to this camera. There we go. Tight. All right. So I was going to do, so we hit voltage, current, resistors, resistance, power. We haven't gotten into, and there's different types of power too. So there's like watts is really considered true power. The power I'm actually delivering, the power that's actually going through and dissipating as heat. When we introduce capacitors and inductors, we can also generate what's called reactive power, power that is stored and then introduced in the circuit as things change with time. And then there's apparent power, which is a combination of the reactive power and the true power, because there's also a relationship in there's not just resistance, there's also reactance, and the complex relationship between reactance and resistance is impedance. So there's a lot of stuff to talk about, and all that stuff gets really interesting when you start talking about alternating currents. But obviously, I think that is something that we need to save for another day. So with that, I'm going to let me think. I think that's it. Next time, I don't like doing I like the whiteboard, but I like to be able to have a little bit more to do with actual circuits. So I may do some screenshots next time to recap this one, and then we'll head off. Maybe I have little circuit simulators we'll show. I guess we'll save everything else for next time. So with that is the second episode of Gears of Resistance. Thank you very much for listening, watching, or whatever you are doing. If you've got any comments, questions, hit us up. Right now, again, this is all off of Steam Power Podcast website. So go to steampowerpodcast.com. You'll find contact us link where you can send us an email with your questions. Also, there's links to like Google Plus page. So if you've got questions, you can launch them on there. And with that, I think we're going to start, I think another about 4 or 5 episodes, feel out different things. I want to try some different stuff. This week just flew by, and I didn't get really to do what I wanted to do in the way I wanted to do it, but I wanted to get something out. So feel free to let me know how miserable that was. But yeah, my little one's over here laughing. So with that, we'll see you next week for Steam Power Podcast, and then we'll be back in 2 weeks for the next Gears of Resistance. And yeah, so that's it. Again, thank you all very much for listening, and until next time, stay quirky.